Look at our overall reaction. Same general concept as that happened with the aldol condensation. The one thing that's kind of important as far as getting the reaction to go forward is that second to last step, number 4. It is that step, the removal of the second alpha hydrogen, which forces or helps push our equilibrium to get us to our final product. Okay? That step is what allows the Claisen reaction to work. So for all intents and purposes, it is identical to the aldol condensation, except that after the attack, we kick out the oxygen leaving group. Some things to consider. Well, we haven't seen this slide yet, right? I can't remember. I just shuffled all the slides around, so we just started looking at it. Okay. So that top case, we end up seeing no reaction. Why is there no reaction on that top case? When you look at the alpha position, there's not 2 alpha hydrogens. So that reaction does not work well. Okay. We need that second alpha hydrogen to draw the reaction along. The next thing you might notice is that in all of the reactions we've looked at so far, what is the base spin? It's been an oxygen, but has it been hydroxide? It's always been ethoxide. And that may seem a bit odd as to why we're using ethoxide all the way through it. Does it matter what base we use? Kinda, not really. Okay, so let's take a look at the reaction shown below. Okay. This is a special case because we've got some interesting things happening here. Most important of which, what pseudo-functional group are we seeing? We have the dione-ish functionality popping up in there. What does that dione functionality end up calling out to your attention then? What do we say was special about the dione? What resonance? I don't see any resonance yet. It's the first step of your Claisen reaction. Deprotonate, the removal of the alpha hydrogen. If we remove that hydrogen, what do we generate? It's drawn up there, so you could just tell me directly what it was. Negatively charged carbon. Okay, so you got the good, easy answer out of the way. Now you got to keep going. What else do we have? There is resonance involved in this. What does that resonance then tell you? So resonance does weaken the nucleophilicity. That's true. Strengthens the acidity of the original compound. So the original compound was actually relatively acidic, as we saw with the pKa on the previous board. The pKa of that is sitting somewhere around a 9. Okay, so that's relatively acidic. Okay. With this compound, we now have a nucleophile that could go through and do Claisen type reactions. It could go through and do aldol type reactions. It could go through and do alkyl halide substitution. I've got a nucleophile. Okay. So that is pretty cool. But to get the nucleophile, what did I have to do? I had to do an acid-base reaction. So we took our base, ethoxide, and we reacted it. What else can ethoxide act as? Just acted as a base. Could act as a nucleophile. Please draw the product if it acts as a nucleophile. I'll give you a second again. So we get 4 products here. We'd end up with 1 product here. How did we shift to getting only 1 product from when we had 4? And really all we did was change the number of steps. Why does that all of a sudden change on us? NaH, number 1, stupidly strong base. Okay. What else is important?
We added it in 2 steps instead of all at once.
We did it in 2 steps. We used a really strong base to deprotonate our, what is that, butyraldehyde? 2, 3, 4. Okay, so that we only had 1 nucleophile. Why did we have to use a stupidly strong base in this case? What's that? To completely react. But with the dione, I didn't need a stupidly strong base. I could have done it with ethoxide. And that would have been a complete reaction. What is different about this material versus... It's an aldehyde versus, not quite, the dione. The diketone is much more acidic due to the double resonance feature. So I don't need to use a stupidly strong base because ethoxide relative to the dione is a stupidly strong base. Ethoxide relative to an aldehyde, not that strong of a base. Okay? So we are changing the acidity of the compound by changing the starting material we work with. Okay? That helps us decide what bases we can use. In the case of the aldol, we used our stupidly strong base to completely form our nucleophile so that we didn't get any intra or inter-type reactions. Then we could react it with our electrophile. Okay, so we selectively controlled when our reaction occurred. If we were going to go through and do a crossed Claisen reaction, this becomes problematic. If we look at the choice of reagents used at that bottom one, what's going to be the problem? How many alpha hydrogen sources are there? There's an alpha, there's an alpha. So when I react it with the methoxide, which one becomes the nucleophile? Either one, which means how many products do I get? A whole lot of a mess. Okay. So if we're going to do crossed Claisen reactions, we have to, just like we were with the aldol, be very careful and selective with the reagents and the timing at which we put our chemicals together. Okay. One of the problems that's going to pop up is that when we use a base, it will completely deprotonate. We have our nucleophile, which could potentially then react with other ester molecules present. So we don't get that same kind of nice, smooth segue that we would have gotten with the aldol. So the biggest way to go through an approach is to pick a starting electrophile or a starting ester that has no alpha hydrogens. Well, if there are no alpha hydrogens, the only thing that can happen is it for to act as an electrophile and be attacked by our starting nucleophile. Okay? So there are some common starting esters that work as good electrophiles. Notice that they all have in common. There's our carbonyl. At the alpha position, what do we have? Oxygen, not a carbon with hydrogens. If we move to the next one, there's a hydrogen at the alpha position. Not quite. The hydrogen is the alpha position. That doesn't count. Okay. We need to have that 1 carbon leeway in between to help with that resonance. Okay. Next one, again, no alpha hydrogens. And the last one, same deal, no alpha hydrogens. Okay. So we can use those to add a single carbon structure, or potentially 2 in the case of the diethyl oxalate. Okay. Kind of a nifty little setup. That dione is special on its own, and we can do some more fancy chemistry after we've gone through and formed it. Okay, and that's what the next sequence of material will almost talk about, because we aren't quite there yet. Okay. Ketones and aldehydes end up being more of a fair game because
least 2 alpha hydrogens.
We got 2 alpha hydrogens. It's a little bit cleaner to do the reaction. I cannot explain for me the life of this. Remember how in the aldol we did that intramolecular cyclization reaction? And it was just standard chemistry. Claisen reaction. We gave it a name even though all it was aldol chemistry. Nothing really fancy. Same chemistry. Okay. For some reason, this guy Diekman came along and did intramolecular aldol condensation that's really Claisen condensation. And because this chemistry is now 3 times removed from the actual original chemistry, he for some reason got to attach his name to the reaction. Okay. So now you'll hear reference to the Diekman condensation. What is it? It's an intramolecular aldol equivalent condensation reaction. Okay. Nothing particularly new or fancy or exciting about it. You're just starting with a really long diester compound that can intramolecularly close down to form a ring. Why does it have to be a really long diester compound? We need to form a stable ring. But we had to form a stable ring in the case of the aldol, and you'll notice the carbon chain looks a lot longer in the case of the Diekman. Why does it have to be longer? It's our alpha carbon happening or reaction happening internally to the Diekman condensation. Okay? So that when we go through and look at our reaction, it is our alpha positions that are looping back. 6-membered is going to be your optimal. Can you potentially form 5? Yes, but 6 is the best way to go.
I can imagine, like, with less than 5, the difference.
Yeah, the less than 5, not going to happen. You're not going to get 4, 3, 2-membered rings. Those are out of the question. But you can go through and see potentially 5. 6 tends to be the standard because you have the most stable chair conformation. Okay. Then we go through and name a whole bunch of more reactions. Oops, I pushed the wrong button. Let's push this button. There is reference. That didn't show up like that. So there it is. If we go through and take a look at these 2 compounds, the top one is referred to as acetoacetic ester. The bottom one is referred to as Malonic ester. Guess what these ester compounds can do? The same thing. You can remove the hydrogen. You now have a nucleophile. What can you react to that nucleophile with? Electrophiles. Yay! Okay. Why are they particularly acidic? You have that dione chemistry happening in between. Okay. This becomes kind of nice because I now have a nucleophile. I can attach carbon structures to the end of that alpha position and I can extend my chain. Okay. You might say that that would look weird, and I would agree with you. You would then extending your carbon chain, but then you have this weird floppy thing going both directions to the other end. You get this weird T shape. And yeah, that does look a little bit bizarre. Okay. But it can end up being very, very useful, not because of, say, that particular reaction, but the following reaction. Okay. So if we look real carefully, in that previous slide, all we went through and did, remove the hydrogen because it's particularly acidic due to that double resonance. We have it react with a carbon electrophile, nice straightforward alkyl halide in an SN2 type reaction. We've now extended our carbon structure with this big old T funky thing sitting on the top of it. And now what happens? What changed?
It won't react now. Because there's only 1 alpha hydrogen.
There's just 1 alpha hydrogen?
Well,
That's the only thing that changed, is we've changed the number of alpha hydrogens?
no, something more.
Something left, I agree with that. What are you saying, Will?
The whole
It's not just something left or a hydrogen. The entire right side of this molecule has disappeared. Okay? That's kind of shocking. Okay? It's an interesting reaction. It's a reaction that happens very commonly in biochemistry. Okay? The byproduct of this reaction happens to be CO2. Stop smelling my breath. Sorry, guys. Okay, we end up forming CO2 in the course of this reaction, and that's one of the things that drives this reaction along. Okay, so now the question is, how does it do it? So we know what's happened, and we know it's important because that's respiration. Okay, we do that, we respire, we release CO2. Okay, in the breakdown of glucose. Okay. How does this reaction occur? Take a minute, work with it, see what you can come up with. First thing to think of, what is the most reactive thing there? The acid. So you might want to protonate some stuff, shuffle some stuff around, see what happens. What kind of reaction are we running? Said another way. It is our nucleophilic addition and elimination. That structure that I've ended that line with happens to be what? The tetrahedral intermediate. What was it catalyzed by? Acid catalyst. Remember, this is the reaction I've been avoiding drawing because of all the stupid protonations and deprotonations that I didn't want to draw out, and I just suckered myself into. Tried to sucker you into it, but too many of you have just been staring at it. So we now have the tetrahedral intermediate. What happens now? What's that? The electrons could cycle back, but do we have a good leaving group? We'd have an oxide leaving group, which would be a strong base in a strongly acidic environment. That's a bit of a questionable leaving group, so fix that. What should we do first? We should protonate. So we'll take the lone pairs from our oxygen. Now what happens if our electrons crash back down? Now we have a good leaving group. At the end of all of that, almost at the end of all of that, we have this structure. Yes? Protonate what? Deprotonate, okay. And I'm going to be a bit evil here. What did I do? I just rotated it. I just rotated a sigma bond. Everybody okay with me doing the rotation of that sigma bond? Okay. And there, we got our final product, right?
No.
Okay, so what's wrong? Okay, next thing I'm going to draw that a little bit bigger. Where is our final product in that drawing? left half of that. No one's complained about it, but just in case you're internalizing it, is everybody okay that I just kind of cut off the rest of the left half of that structure? Okay, just making sure. So that left half needs to somehow stick around, okay, where that right half needs to disappear. And I actually told you what the other product was. What was the other product? CO2. Where is there CO2? Could deprotonate that alcohol, so we'd need something remotely basic floating around in solution. How about that oxygen that I happen to draw right next to it? Any complaints right away? Okay, I'll accept that. And I'm going to change that arrow in a second, so don't draw it. Really? No complaints? What I just drew right there. Thank you. This is an intramolecular deprotonation. What did I say with intramolecular deprotonations? They do not happen because too far apart. Our transition state ends up being a 3 or 4 membered ring, which structurally does not happen. Am I recording? Good. Is this a 3 or 4 membered ring? 1, 2, that's 3, 4, 5, 6. What kind of ring structure is that in our transition state? Cyclohexane. What do we know about our cyclohexanes? Really stable. Am I allowed to do the intramolecular here? Yep. And there is evidence to suggest that the intramolecular acid-base reaction does indeed occur. Okay. The next part of this. What do we do with the electrons in that hydrogen-oxygen bond? Okay, the arrow that I had initially drawn was just taking it to the oxygen.
Carbon.
Which carbon?
The central carbon on the oxygen-oxygen bond.
Central carbon. Let's just draw the arrow. Is that what you're saying?
Yes.
All right, so what you're suggesting is not going to the carbon, but to the bond. This gets pretty cool because if we look at our Lewis structure for carbon dioxide, what is it? We need that extra double bond. Okay, so this would be forming that extra double bond. But what's the problem with that? That carbon would then have too many bonds. So what do we have to do? We have to break a bond. What bond do we break? Why the carbon to carbon?
It's not as stable a product.
There's an interesting question. The highest energy bond in that case would very likely be the carbon-oxygen pi bond. Okay. Does that do anything as far as stability goes? No. Okay. And that might be our first guess, but if we said that, then the reaction doesn't occur. Okay, fine. Then we say the reaction doesn't occur, the lab says otherwise. So something else has to break, and we know what that something else is. It has to break that carbon-oxygen or carbon-carbon bond. It has to break that carbon-carbon sigma bond. How often do we break carbon-carbon sigma bonds? In fact, have we ever broken a carbon-carbon sigma bond? I don't think we have we? Huh. That's a bit weird. We're breaking a carbon-carbon sigma bond? That is something that is so rare we have never even seen or done it. Why would we be allowed to break a carbon-carbon sigma bond? What is the result? What do you mean resonance?
Of the negative carbon that you forgot to drop in.
We form a carbanion. Okay. We form CO2. What is special about CO2? It is an insanely stable molecule. So insanely stable, what is our primary source of greenhouse gases? Carbon dioxide. It is so stable that we can't get it out of the atmosphere once we put it there. That's why it's a problem. It is incredibly stable. If it is incredibly stable, what does that mean about its energy? Very low energy, which means we've got a driving force now to produce this product. Okay? CO2 on its own can't be the be-all, end-all. We're also going to have to show that the other product formed a stable species, the other half of our molecule. Why is that molecule stable?
Because you have opposite charges. The oxygen is more likely to dump that hydrogen and steal electrons from the carbon, and then the other negative carboxylic hydrogen.
What's happening at the very end of that reaction? You want to say that a little louder? We have the keto-enol tautomerization. Okay. That stability is one of the things that is also driving the reaction. The reaction or the system will very quickly tautomerize back to the ketone, and we will pick up and put a hydrogen on at that last position. This reaction is known as a decarboxylation. D for remove and carboxylation because we lost a carboxylate, the CO2. Okay. Super common reaction in biochem. You see it happen all of the time. It's one of the natural mechanisms for producing CO2 in the decomposition of glucose to form energy. Okay, your glycolysis reaction. Okay. Also incredibly useful for synthesis because I've now converted my starting compound, an alkyl halide and this diester compound, and I've got a carbon nucleophile that I can very quickly ditch another piece of the molecule, simplify my structure down very quickly. The two starting materials commonly used for this type of synthesis, before I delete all this because I spent some time drawing it, I don't want to delete it right away. Anybody need a copy of that? Fine. Acetoacetic acid and malonic ester. They're referred to as the acetoacetic acid synthesis or the malonic ester synthesis. Both of them are just starting with those compounds to generate the carbon nucleophile, which can react with a carbon electrophile in the alkyl halide form. We've done a carbon-carbon bond formation, and we can kick off a big section of the group that we don't have to worry about anymore. We still have the carbonyl compound, potentially even the ester. Everything's fine and dandy. Kind of a cool little reaction. Let's see, does this slide show it? This. We'll come back on that last one. Can I decarboxylate again? Okay, so as a sort of hint, let's go back to our mechanism. Shnikes. What if I had my malonic ester? Okay, or actually it would at that point be a carboxylic acid. Could I decarboxylate a second time? Okay, why? We'd have CO2. Okay, and the mechanism I drew out, what was the other big component? Once we lost CO2, we had that resonance contribution. That's what stabilized and allowed the CO2 emission. Do I have a resonance stabilization in the remaining piece? No. Can I do the decarboxylation again? No. The only way the decarboxylation works is that if you have that ester or acid functional group, beta to a ketone. You need both, or beta to a carbonyl. If you don't have that other piece, you can't do the elimination because you don't have that ketoenol tautomerization that's also helping the reaction along. Okay? We can't form just a negative carbon willy-nilly. It has to be resonance stabilized. Okay? So in the acetoacetic, whatever that big long word, actually I said it right that time, acetoacetic ester synthesis, all we end up doing is putting on a ketone. You'll notice that we've extended our carbon structure by 3 carbons. Okay, kind of nice. We've added 3 more carbons to our structure, relatively tiny pieces, but nice and simple.
Would, if you, the product of that, would that ever act as a nucleophile and make us submarine with carbonyl?
Try that again. So what carbon are you saying is the nucleophile?
The bottom of the pi bond.
While our pi bond can act as a nucleophile, when does it act as a nucleophile? When it's reacting with reasonably strong electrophiles like boron, like mercury, okay, like bromine. Okay, we don't get very good nucleophilic characteristic to be able to attack the carbonyl there. Okay. We could potentially turn the alpha position of our carbonyl into a nucleophile and tweak the chemistry of that alkene to get an attack.
So I was thinking more like the Diels-Alder.
Bad idea for Diels-Alder, because the Diels-Alder reacts what 2 pieces?
You need an alkene.
You need alkenes, you need a diene and a dienophile. That's 3 pi bonds. There's only 2 pi bonds there. So in the acetoacetic ester, we end up with a much longer carbon chain, and we still have the reactivity of that ketone. In the malonic ester, we end up with 2 carbons in our structure and the acid functional group. So it's a way to get an acid functional group into our structure. Okay. Kind of a neat little synthesis on those. Typically what you end up doing is causing some chemistry happening at that center alpha position of your dione-like functional group. Okay? Questions on that? Well, isn't that nice? Protecting groups for carboxylic acids. I don't think I even asked a question. Did I? Maybe I asked a question in the smart work about protecting groups of carboxylic acids. I won't ask a question on it on the test. I just want you to be aware of it, so I put a question on it for the homework. There are a variety of ways that you can protect a carboxylic acid. Most of them involve turning it into an ester. Esters are much less reactive because steric hindrance is you buried the oxygen behind some more carbons. Okay, so there's a lot of steric hindrance there. Once you've formed the ester, it can be difficult to reverse the reaction. So some of these get a little bit more interesting as far as reversibility goes. I would say probably the most interesting, to me at least, would be number 3. Why would number 3 be an interesting one as opposed to any of the others? The other 3 all involve what chemistry? At least in the removal. It's acid-base. Okay? It's just acid-base moving through the tree of your acid derivatives. Question 3 there is a lot more interesting because is that strictly an acid-base reaction? No. Not only is it not acid-base, we're using hydrogen and palladium to break what bond? Not only a sigma bond, but what sigma bond? a carbon-oxygen sigma bond is being broken with hydrogen and palladium. When have we used hydrogen and palladium before? To reduce alkenes, to reduce pi bonds. Interestingly enough, the palladium or the hydrogen and palladium can be used to actually break that oxygen-hydrogen sigma bond due to the polarity within that situation. So, kind of a neat little reaction there. I just thought it was interesting. Okay. After that, we got a bunch of optional material in 2 minutes, so that's probably all the time I really want to spend on it. You can look at protein degradation. So proteins, big string of amino acids. One of the things that biochemists will want to do is to figure out what amino acids are in that protein. So we'll go through and run it under certain conditions. Depending on those conditions, it will break the protein only at specific types of intersections. Okay? So the rest of this section is pretty much talking about how we can disassemble a protein in, say, a biochemistry class based off of the organic chemistry involved in proteins. Okay? Beyond that, I don't really care to talk about it as I recorded. That was pleasant. Okay? So there's some famous degradations. Your Edman degradation, you're using phenyl isothiocyanate to go through and break the protein structure down. So you can end up selectively removing amino acids, which is kind of nice. So you get all sorts of fun hydrolysis there. You can use DCC to synthesize peptides, super exciting, fun little mechanisms. Why would they talk about all these mechanisms now? Proteins have what kind of linkage in them? Yeah, don't you love that? Thank you, biochemists, for that one. What bonds do proteins have in them? Oh, they're polypeptides. You mean they're amide bonds from organic chemistry? Why'd you have to invent a new name for a bond? It's the same thing. Okay. It's an amide bond. We've talked about amides within this section. All you're doing is trying to degrade that bond. For those of you who said polypeptide, I wasn't trying to mock you. I apologize. Synthesis, all sorts of fun stuff like that. So if you would like to, you can go through and review that material. I won't ask any questions on it. But yeah. You can see my opinion of biochemists, which is awesome because that's what the class I teach too.